Sorry for the slight technical glitch. Is my screen visible to everyone? Okay, perfect. So as I was saying, so this particular stable diffusion model was released in August 2022, and it was released by a company, London-based startup called Stability AI, and they keep on releasing different type of image generative models out there. And specifically for this stable diffusion, it has taken the entire computer vision community by storm, right? Like they were amazed as to how can you generate visual hallucination images, right? Whatever you think, yeah, and a model and an AI model can immediately generate it within seconds, right? So just to give a quick introduction about myself, my name is Suman Choudhury. I am a data science solution consultant at Sahaj. I generally work in the areas of computer vision. My areas of expertise generally lies in the finance domain, e-commerce, fashion, and then I also work in the cybersecurity domain also, right? So having said that, let's deep dive into stable diffusion and what it is. Is the screen visible now?
Yeah.
Yeah, it is.
Okay. Okay, perfect. So let's start off with something like, let's think of something first, right? Maybe let's think of an animal, right? Maybe a pug, and then let's think of an activity. Let's say a person baking a cake, right? So now if I ask all of you to just think for a second that a pug is baking a cake, right? Generally, you won't find such type of images on the internet that pug is baking a cake. Like it's more of a visual hallucination that you see out there, right? But stable diffusion, whenever you type in for a particular text called a pug baking a cake, right? It immediately, within a fraction of few seconds, it generates a picture that actually represents a pug baking a cake, right? Wonderful, right? It doesn't stop there, right? I tried out with more few examples that I wanted to show you, right? So like on astronaut riding a horse, it's a rare event. You generally don't see it, right? But then just think that model is capable enough to understand what that particular text or context was and was able to generate this image called an astronaut riding a horse, right? Just look at the right side. This is a particular text that we gave, an old person wearing trendy glasses, might have a mystic background, some neon color light, and in 4K HD format, right? And within a fraction of few seconds, it was able to generate various images of old person, some person wearing wearing a particular sunglasses and all, right? So seems unbelievable, but this is how the model has been able to achieve near, almost close to reality based images out there, right? So what are the possible use cases that we can think of specifically with regards to stable diffusion, right? I tried to dive into it, and then the answers that I got is that, like, think of all the digital arts that you see out there, right, in the open like market, right? A particular, let's say if I say an old Vatican city and an old city, immediately it is able to generate a digital art within seconds, right? Talk about image inpainting. What is image inpainting? Given a particular picture that you have, let's say a particular dog that is sitting in a particular bench, you can replace that particular object out there and then replace it with the other object. In this case, it's a cat, right? So even even if you see both the images, right, the striking realism in both the images is like indistinguishable, right? So the capabilities are very huge out there. This is another which has been creating quite a buzz. Like given you, if you have certain images with you, let's say 4 to 5 images of yourself, right? There is a particular tool called, or a particular website called Dreamboat, which has been released by Hugging Face. Hugging Face again, it's an OpenAI company where you can actually upload your images and then train up your model. It also provides you different endpoints out there so that you can actually use your model. Once you upload there, you can use their endpoints to show the inference, right? So they have come up with a particular tool called Dreamboat, where given some images that you have, you can actually create stunning AI pictures for you, right? So here in this case, we have given some Ramcharan. So he is an Indian superstar. We have given some 4 to 5 images of him, and the result that you see on the right side is the AI images that it has generated, right? Quite visually, quite stunning. So now you understand that the possibilities for this particular model called Stable Diffusion is enormous, right? But how can we go deep dive is the main motive of this talk. So I would rather first talk about the 3 main components of Stable Diffusion. The 3 main components generally that we find in Stable Diffusion are as such. One is called as the denoiser. So what does the denoiser do? Like now we are looking at a very satellite view, right? Then we'll go deep dive into each and every component out there. So let's first talk about the first component called denoiser. What it does is that given a particular image that has a lot of noise with it, right? Noise is nothing but the missing of a pattern, right? When you corrupt a particular image with noise, the image becomes much more blurry, not able, human eyes cannot visibly look at it, right? The purpose of denoise is to remove the noise from that particular image and give you a better image at the output, right? Let's talk about, that's one part which will dive deep into it. Next, let's come to the autoencoder. What does the autoencoder do? It takes up an image as an input and then gives you a visual representation, which is very very small in size, but then it also has all the qualities that the input has, right? So you may say that autoencoder's encoding technique, it actually compresses the images and gives you a visual representation of that particular image. So that was the 2 part. Last but not the least, let's come to the conditional mechanism, right? Conditional mechanism is such that, like, when you say a growling cat or an astronaut riding a horse, right? You want the model to understand what you are speaking, right? The model doesn't understand the text. So you have to convert that into a certain way that the model understands what you are trying to, and give the information to the model, right? So these are the 3 parts on a separate basis. We like I first showed you the satellite view. The Stable Diffusion is mainly built up of these 3 components. Now let's dive deep into each and every component first, right? First, let us have a look at the denoiser part. So now, before we go into the denoiser, let us grasp some concepts first. Let's say we have an image out there, right? And the one that you see at the top left corner is an image of a flower, right? That's a very perfect image. But then when you chip in some amount of noise at every iteration, the one that you see out here, right? And that has some amount of noise that has been chipped in along with the image. The resultant that you see out there, it's a bit distorted images having some amount of noise, right? At the next step, you imbibe more noise into it, then it becomes more and more unclear, and then it becomes noisy, right? As you go down the steps, the quality of the images gets distorted, and after a certain point of time, you would rather find a fully noisy images, right? So basically what I have written out there, let's say the input is being contaminated with some additive Gaussian noise, right? So at every step in place, you are adding some amount of noise to the image, and then finally you get a particular noisy image out there, which has image, but also it has the noise component in it, right? This part is just a reflective of the part. Let's say I'm taking up a particular cat, right? After we have been adding some amount of noise out there, so you see some amount of blurriness or the distortion that came into the cat, right? We add more and more amount of noise, you see that the cat gradually turns to disappear, and then finally we get a fully random noise, right? So this part is what we call as noising, or what we call is adding noise to the image, right? Now think of the reverse part, what we call as the denoising. So conceptually, so it's just taking up that particular image that is noisy, and gradually you remove the noise at every step, right? So eventually when you remove the noise, you get a more visible output, much more clearer output. At the end, you get the original image back, which is devoid of any noise, right? But now let's think for a second that ideally, you would like there are many ways that you can actually remove the noise, right? Yeah, have you been in computer vision technique? There are many ways to remove those noise from an image, right? This can be Gaussian, like Gaussian filtering, median filtering, right? Replacing that particular with or what we call it as the median smoothing, right? Take up a kernel and then put the value accordingly so that it removes the noise. So there are many techniques to it. But then the question that we generally have to pose is that what if, like, which you would see like at the end of the particular lecture, where what if the input was just a noise, right? How do you remove noise from that particular input, right? The model has to understand something. So it is that case, in that case, what we thought, like the people out there, researchers out there at Stability AI, what they thought is that why not build up a model that tries to predict noise, right? So given a particular image that may or may not have some amount of noise, you would pass in that image through a particular neural network model. The output of the model would be nothing but it predicts that, okay, this is the amount of noise that you have, right? So in that case, we come up, and the first step that you see in the denoiser technique is this particular architecture, right? So this particular part is clear to you, where we have a particular image, we chip in some amount of noise, and then finally we see a fully noisy output out there, right? Now think of the reverse case, where you have a noisy image, you pass it through a particular neural network. Specifically, we use a UNet network out of it. I'm not diving deep into the UNet network because that is itself a particular lecture in itself. But the output of this particular neural network would be to predict the noise, right? Now, be with me at this particular slide, right? So now think of this particular case where you have a particular cat having some amount of noise. You then pass it through a neural network, which predicts how much noise that would be out there, right? So now in the next step, what you do is that you subtract the noise from this particular input, the noisy input, right? So what you get is a much more refined and less noisy output, that image that you get, right? You pass on the image again through the UNet, it again predicts how much noise is there, right? Again, you take up this noise, subtract this noise from that particular input, you get much more refined input, and this process continues until you get back the original image, right? So now you understand that you have created a model where, given a particular noisy input images, your model would be able to predict what would be the noise, and then at every step you subtract the noise from the noisy input image, and then you get a less noisy input, right? And you continue this step until you get the output, right? Seems very like it's a very simple architecture that you can think of, right? But now, what are the problems out there? Now, every one of us out there in this room and who are being online out there have a iPhone or Galaxy or any phones out there, right? Nowadays, the cameras have evolved so much that almost everyone has around 40 megapixel camera, right? iPhone might have a 50 megapixel camera, right? Each of those cameras has the capability to click around 2048 cross 2048 pixel images, right? Which, like, when you multiply this to all those pixels out there, you have almost close to 4 million pixels, right? Also think about this particular UNet structure. I'm not going deep dive into that structure, like a particular architecture, but then think of that particular UNet, which has almost 800 million parameters to train upon, right? So now when you pass all those batch of images through that particular network, which has so many million parameters, when you do that, the computation would be very large and the training time would be very slow, right? And it would take many hours to train up a model where, you given a particular image, you remove the noise and get the particular output. It will take a lot of amount of time, right? So the bottleneck out here, or what we find the problem out here, is that the sizes of the particular image is quite large to cater into, right? So how do we cater into those sizes? It is here we come to the second concept, what we call as the autoencoder. Remember, like while at the starting of the lecture, when I said autoencoder, what it does, is that it takes up an input, it takes a particular input and then tries to give a visual representation, but at a much more smaller size. Okay. Yes.
So before you go to the autoencoder, I would like to ask a question about the denoiser.
Sure.
So previously we have seen models, neural network architectures were given an input image. The neural network directly gives you the noiseless image. Now this is new, that the neural network is trying to predict the noise which is being subtracted from the input image. Is there a benefit to just predicting the noise instead of just giving you a denoised version of the image?
You will when we go to the end of the lecture, right, we'll actually understand why do we do that. There is a particular specific reason to that. I'm keeping your question at the end so that I can answer that, right? Because we, like the people out there, had thought of a particular process where, let's say, I'll give you the answer partially. Let's say in a testing time, right? You don't if you play around this particular model called Stable Diffusion, the only input that you have is just a text, right? How do you make the model understand that what input what this particular text is, right? So it is at that particular testing scenario, the model starts with a random noise, and given that particular input, it configures in such a way that it generates an image out of a random noise, right? You get a particular definitive images from that particular noise that it has created. So it is in that respect, the creating a particular predicting a noise is very necessary, which will, like as I go down the architecture of autoencoder and conditional mechanism, it will be much more clear to you.
So it will be the inverse of state.
Yes.
Something like that.
Yes. Yes. Right.
Yeah. I have one question.
Sure.
Like,
please.
how to decide this N? How maybe?
Yeah. I think it's Ranjit, right? Good question, Ranjit. So, so the point is that here, like, it's all hyperparameters that you have to tune around, right? Some I'll give you the architecture where the people have gone through the paper. What they do is that ideally they take around 50 to 75 steps to train around your model. Of course, this in order to generate those images, you have to play around those numbers so that you can come up with a optimal number, that how many steps would be enough to generate a particular picture from your noise.
Okay, so suppose we have decided n equal to something like 100, and then we have trained the network. Then at the inference time, now suppose we do not know how much noise is there in that particular image. Then how to give that thing to the model? Like we do not know that we have to start from n.
Correct. Yeah. So I all the questions would be very clear. Like as I go down the lecture, there is a particular slide dedicated for training and how do we do that. In that step, that would be very clear to you.
Okay, fine. Thank you.
Thank you. Okay, so now let's move to the next part, what we call it as an autoencoder, right? So what is autoencoder? So as I said, autoencoder, to talk it at a very high level, it takes up an image which is having quite a big size, and then it converts into a visual representation which is much more compressed in size, right? So let's say if this particular cat that you see out there, that is almost 2048 cross 2048, what we get at the output is a visual representation, and this visual representation is what we call it as a latent. And this particular visual representation, or what we call as latent, it would be of very small size, let's say 64 by 64. But then it would be a visual representation of what this, or it will contain all the relevant information that you require to identify a cat, right? And this is what a variational autoencoder, or in general an autoencoder, what it does, right? So now, if I go, this is a bit out of scope, but then I wanted to talk about this. So if you talk about an autoencoder, that consists of an encoder and a decoder part. So as I was saying, right, given a particular image of which is of a much more bigger size, it would rather pass on through a series of convolution and convolution networks, and then finally you would go by the downsampling, where you would rather reduce the amount of the size that it has, and finally you would come up with a visual representation which is much more smaller in size, right? But then it has all the information related to that to represent a particular cat, right, of 64 by 64. But then you also have a decoder. So now that you have created an image which is of much more smaller size, then you want to again generate that particular image. So think of this case, right? You are actually building up a compressor engine, where given a particular image, if you have the encoder part of it, you can actually get that particular image in a much more smaller size. And also you have a decoder where once you give that particular visual representation, which is much more smaller size, at the output, you will get back the original input, which is the cat, which is of the original size. Okay. So now, remember the problem that we talked about denoiser. The problem was that the sizes were huge, and then if we want to pass in through that image and then denoise it, it would take a huge computation size, right? And it is at this case where we chip in the autoencoder, right? So what we do out there is that a particular cat, which is of a higher dimension, I convert that into a latent space, which is of smaller dimension, which is just 64 cross 64, right? Now, corresponding to this, now think of this as a cat only, but a smaller representation of a cat. Now, what you do is that you chip in some amount of noise, to contaminate that particular input. So now you have a contaminated input of that particular latent, not that original image, right? Now, once you have, and this process continues till ti time steps, right? Of, as you saw in the noising part, you keep on contaminating the input with certain amount of noise, right? Now, once you have that contaminated input of that particular latent, you pass it through a unit, which actually removes the target of that particular neural network is to predict the noise, right? So at first step, given this particular contaminated input, when you pass it through the unit, it predicts the noise. Then you subtract the noise from that input, you would update the input. Now it is less noisy latent. You again pass it through the neural network, you get the prediction of noise. You subtract that particular noise from your input, you get much more lesser latent. And at a final stage, you would find out, like when you have done a certain number of steps, you would rather get a particular latent which doesn't have much noise in it, right? And now this particular latent, once you get it, then you pass it through a decoder. So now your decoder will again convert that into your original image. So what we have done out here, we did not pass the original image to the encoder, and then the trainer tried to predict the noise at the decoder, right? Because it would have taken a lot amount of time. But what we have done out there, we converted that into a small latent, right, which is much more smaller in size. We contaminated that latent and then finally got that particular noiseless latent, and then we converted that into a decoder. Using a decoder, we converted it in original image. So in a way, we have achieved with much more less computation power, because right now we are not dealing with 4.1 million pixel. We are now dealing with just 64 squared, that is close to around 3200 pixels around, right? So now we have come to the two architecture that we understood, right? One big thing that still remains to be answered is that given a particular image, right, the model understands the visual features, right? If you provide this image, it understands that there is some animal. It doesn't understand an animal, but it understands, okay, there is some object which looks like this, right? But how do we make the model understand that it is a growling cat, right? That's a particular word that it belongs to a cat or something, right? Or it's growling out there. So we need some mechanism to make the model understand what it is learning. And thus comes the third concept called conditional mechanism, right? So we talked about the denoiser part. We talked about the autoencoder part. Now we come to the part where we stitch or where we understand what is conditional mechanism. Okay.
Autoencoder is nothing but like if we compare with DCD transformation, discrete cosine transformation, and invert
DCD. It's more like any type of transformation where you take up an image and then compress it and then you again expand it. It's like a bottleneck layer, right? where you have a big image, you can't experiment it out with big image. And this is why, so I was not talking about that UNet. UNet also has a particular, the name UNet came from that particular U-like structure, right? So to the left part of U is nothing but your encoder, which compresses your image or to a visual representation of much more smaller size. The right side of the encoder is the right side of the unit is a decoder, which again upsamples it and brings it to your original size. So this is how you generally look at any type of AutoEncoder network, which contains an encoder and decoder, which compresses the image and brings it back to the original size, right? So now let's.
When you thought about the AutoEncoder,
Sure.
it adds the layer of attention. What if you use attention before? Like, as you know, attention also have RNA network and CNN network. So instead of denoising, if we pass attention, so what will happen if you remove denoiser and add attention?
Yeah. So what, like the question, one of our guests that he asks is that what if we remove those denoiser and then add attention? Ideally, if you like, the reason why I did not show that particular architecture, it would be much more time taken and much more complex. So just to answer to your question, UNet, what it does is it takes into account the multimodal attention. So what do you mean by multimodal attention network? Ideally, is that given if I have a picture of you, let's say, you have a particular person, right? What a multimodal attention does is that it would have a particular filter, attention filter, what we call it, where at a one particular attention filter, it will ask to focus on just the body, right? And let's say you are standing right, right, like the mountain is behind you, and then you have a sky, right? One part of the attention filter will ask the model to focus on just you, right? So the attention filter is on the body and it just focuses on you. Another part of your attention model will focus on the background, which is your sceneries. The third part of the attention model will focus on the sky, right? So if you look at the unit architecture at every stage, they have chipped in the attention model. And ideally, if you have gone through the vision transformer, you would have got a key value, QVQ key value pair, so that you make the model understand what are the things that it needs to focus on. Does that answer your question?
Yeah, kind of.
Okay.
And one question is, like, I want to understand, till now the things we have heard, I find this is similar to a GAN. You feed in a noise, you get a image as input. Unit thing, I kind of feel it very similar to a GAN, where you feed in a noise and you get back an image. And just it is based on an autoencoder. You just plug in an autoencoder to read the image. That's it. But other than that,
maybe a counter argument as such, like just think of a GANs, right? Even if you want to train, like GAN is nothing but an image generative model where you should have different type of images. Like, and one quick representation of GAN while I was working on other projects out there was given a particular image out there at, let's say, like I was talking about a particular fashion project while talking to Ravindra Babu, is that we actually had a project where we had a particular image or a particular model wearing a kurta, right? Now you want to replace that image of that particular kurta with a certain other image out there. So in order to replace those other image, or like, let's say, if you have a kurta, you have a plain kurta out there, you want to put in some amount of polka dots as a pattern out there. So these are the things where you need to have a lot amount of polka dot images as a like to be given for your training to your generative model. And this is much more like a more specific domain specific problem that comes out. Like, let's say if you want to, it's a real problem that I was talking about, right? Let's say if you want to change the pattern of a kurta, you also have to chip in different type of patterns that you want to generate for that particular GAN images, right? In case of a stable diffusion, what you see out there, all the images that you see in the normal world, right? You don't have to specifically think about what you need to train. Basically, you are giving all the images and the meta information to the model. So the three architectures that you see out there, each of those particular architecture are being trained separately, and then we stitch them together. And if you look at each of the architecture, talk about the denoising part, right? In order to make a good denoiser, what you did is that you took took up all the images that you had in the internet, trained your model in such a way that your model becomes so much robust that it is able to predict the noise out of it, right? So you are not restricted by the domain, and in a way you are allowing your model to be more generic to any of the use cases, right? You are not being restricted by the domain, or you don't need specific data. Here also you need a lot of data, but then you are giving all the data that are relevant out there in the internet. If you have the right format, like let's say you have a particular image out there, you contaminate with the noise. So those type of images would be abundant, right? If you want to just learn the Denoiser architecture, you would rather train that particular architecture in a separate way, right? You would give all the images and let your model be much more customized and much more robust in predicting what would be the particular noise output out there, right?
Yeah.
Okay, so now we come to the third part, which is quite important, and this was being this is the main backbone of what we have been talking about, right? And what we called it as a conditional mechanism, right? So we have a billion of images around the internet, right? And what if we take those images and their metadata? Now, what do I mean by metadata? Like if you look at the top left or the left side, like this is a picture of a swan. So what we call it as a graceful swan. So this information is what we call as a metadata for that particular image, right? Let's say for a train or rushing trains, right? So you have the images and also all the metadata corresponding to it, right? What do you want is that you want to train up your model so that the next time when you type in a particular word or called a graceful swan, it understands that what is the image or the understand at the back of the training that what it is actually talking about, right? Now we have an abundance of images, a billion and billion of images out there in the internet, right? So what we do ideally is that we pass in that particular image through an image encoder, right? And we get one particular encoding of that particular image. We pass in that text, the graceful swan, into that particular text encoder. We get another text encoding of that particular graceful swan, right? The next step would be to do an element wise multiplication, or what we call it in the mathematical term, the dot product, right? We do an element wise multiplication, and then we get a particular encoder or a particular a particular image encoder, the value out there, which is nothing but the dot product of both these, right? Now, if I try to draw out a map out there, right? Now, when you are training for millions and millions of images, right? A question that comes to your mind would be, what would be the loss, right? Any type of model that needs to be trained has to tackle into some amount of loss. How will it optimize this experiment so that whatever you are trying to achieve, like let's say next time it says a graceful swan, it is able to understand or generate that particular encoding out of it, right? So this is a particular map that I've tried to draw. So in the left or the bottom left side, you see an image, and in the right, you see a different type of encoding out there. Graceful swan, a rushing train, Virat Kohli, and Facebook, right? So ideally, what you would want is that the product or the dot product between the graceful swan and the image of the graceful swan, the value should be as high as possible. And the one that let's say graceful swan and a rushing train, the value should be as low as possible, right? And what does it say is that the contrastive loss, or what you would rather see at the diagonal elements, if you take up just the diagonal elements where the contrastive swan and a graceful swan image and the text out there, these would be quite high, right? The combination or the addition of all those parameters out there in the diagonal element minus all the off diagonal elements, right? So the value should be as high as possible. That means the value between the graceful swan and the one rushing train corresponding to their image, that particular diagonal value should be as high as possible, and the off diagonal value should be as low as possible. And this is what in loss term is what we call as the contrastive loss, or what you generally find it as a paper as contrastive loss image pre-training. So that was a paper that came out, right? And that is the basic idea behind that. So now next time when a particular person just types in a beautiful swan, right, instead of a graceful swan, it understands that there is something related to a particular swan, which is maybe beautiful or something of white color swan, and it will generate a combination of an image and text encoder that would be representative of a particular graceful swan. And this lies, or this actually inculcates the basic fundamental of what you need to drive in to get your output, right? So now when we understand both denoiser, autoencoder and clip mechanism, now it's time to understand, now let's tie them all together, right? Now, when you tie them all together in the training part, and maybe like it is in this context, Ranjit, I would also love to answer your question. So now, given those images, now just think of those images having billions and billions of images on the internet, right? You take up those images, individually train autoencoder, the diffusion conditional mechanism, and the attention mechanism. But in this particular training, what you do is that given all those images, you pass it through the encoder, you get a small latent space, a visual representative latent space. You combine it with, contaminate it with the noise. You then pass in that particular latent, but this time you also pass in the information that you want to pass in, right? In this case, for this training, what does it represent? A growling thread, right? As I told you, in the previous slide, all those information would be there, right? A swan, a graceful swan. Just like here, you would rather put up those images, and here you would put up the information, the conditional mechanism or the conditional information that you want to chip in, right? Here in this case, a growling cat, and then corresponding to this latent and the information that you chip in out there, in that particular unit, you try to say, okay, this would be my noise prediction. Now you get a noise. Now this particular network also understands that, okay, I have to predict the noise, but also now I have that leverage to understand some amount of information that are being supplied as some supplement out there, right? A conditional mechanism actually tells you that this is a growling cat, right? So now it predicts the noise with much more higher probability, and much more with much more confidence, right? Now you remove that particular noise, update your input, you get a less noisy latent. Then again, you already have the conditional, embedded value out there for a growling cat. You again pass it. Now it again predicts the noise, but with much more confidence. You again remove that particular noise, and then finally you get a particular latent which is almost devoid of noise, and then you finally pass it through a decoder to get your original output, right? And this is how you'd go for a training, right? Now just think of a testing. Now comes the real world scenario where we generally play around with a diffusion model, right? Where we see a particular, let's say someone has just typed in a growling cat, right? It is in this case, now I wanted to answer your question. So now he has a particular, that particular model will start off with a random noise. It passes through the encoder, which will convert that into a smaller latents. It will, you already have a growling cat, which you pass it through a multimodal encoder or a conditional mechanism CM, which converts that into an encoded features. It then passes through the denoiser unit, which predicts the noise, right? Now it predicts the noise, it gets subtracted. Like you update your input by subtracting the noise. You keep on doing that until and unless you get a particular output, which is being represented by out here, which is being as a like a refined latents. And then you finally pass in through the decoder, which gives you an input of this growling cat, right? So very interesting, right? Now you have just given a growling cat, but from that particular noise, because your model is already trained enough to understand or to remove the noise, you can just generate a particular image from those random noise, right? And the step that I've written, that every time when you again type in a growling cat, because the initialization would be different, right? So the initialization, even the growling cat, maybe the next time the encoded features may be different. It is in that case, when you again type in, or when you again run the model, you will get a separate different images of a growling cat, or likewise at a growling cat, right? So this is the basic idea as to how you can play around with stable diffusion and generate a lot amount of images just from the textual information out there, right?
So, I have one more question. So
Yeah.
since during inference, we need to pass that noise now n times, so it may create model very slow. Like we need to pass n times the same thing.
I did not do you need to pass that noise n times, as you were saying?
Yeah, so every time, suppose first time you pass like noise to the model, so model will give you some output. Now next time again you have to pass that particular thing to the model. So
No,
it
so maybe like we are like there might be a miscommunication out there. So let's say when if you pass in a growling cat, right, Ranjit? So what the model does is that it takes up a particular random noise, it generates a latent, and then corresponding to that latent, it keeps on removing the noise from your particular latent until and unless it is confident enough to show you the input which is much more as close to the image that you want, which is of a growling cat, right? You don't pass in the random noise. This is not in your hand. This is something the model takes up as an initialization. It takes up a random noise initialization at a starting point. The only input that you get if Ranjit is just the text. It says the growling cat. It will take some noise within, and it will try to make some sense from that particular noise into a corresponding particular output, which is a growling cat. So the next time when you again type in a growling cat, it will again take up a random noise of its choice of some initialization. It will pass in through the latent. It will denoise that particular latent, and then finally, when it passes through the decoder, it will generate another set of images which is based out of growling cat. And this is the reason why every time when you put in a growling cat, not only the encoded features may be different, the initialization of that random noise will also be different.
yeah, I understand your point, but if you see since denoiser will be used n times, like, and denoiser is again one model, so
Yes.
that take time and it will slow the like process. So
Ideally, like what we found out, like ideally what I understood from the literature survey is that because then what Ranjit, if you just recall what we have talked about earlier, encoder, what it does is that given however bigger the image is, it just compresses the images to a much more smaller size, right? Even though if you go for n iterations, the computation that you require to denoise that particular latent, which is of much more smaller size, would be much more smaller than had you actually passed in the original images. And this is the only reason why we use encoder decoder technique, right? We don't want our even the inference model also to pass in the original or the bigger dimensional images, right? We would rather want to take up that particular visual representation of a smaller dimension and then remove the noise. And then once we have the defined latents, which is of smaller dimension, since we have already trained a decoder, we would again get back the original or what we want, an original size dimension as in when required, right? So, and this is the reason why we generally use. So to answer to your question, ideally it should not take up like even in the inference time, it does take a few seconds, but should not be that long that you would rather have to wait for minutes and minutes. Ideally, it should be in a matter of seconds. Ranjit.
yeah, understood. Yes.
Question. Random noise is just random. Right? It has no association with whatever test you are doing.
Correct. Yes.
So.
So let's talk about the computational power requirements, and this may vary, right? Like we still are, because Stable Diffusion did not talk much about those. But when I went to the literature survey, and then when I found out, what they have said is that it's not V100, it should be A100. A100 is around 40 GB GPUs, right? 40 GB of GPU power RAM. So ideally, they take around two A100 GPUs for your training. Testing can be done on a low powered GPUs. That's totally okay. Like I think most of you might be familiar with the Google Colab Pro or Colab. I personally have tried out Stable Diffusion many times and got a lot amount of images, generated a lot amount of images. Should not take more than 20 to 30 seconds to generate images for you. So it has actually democratized AI in a way that the normal people without any high-end GPU laptop can also play around with Stable Diffusion. Just in case if you think, okay, let me train up the model, Hugging Face also provides you that opportunity called Dreamboat, where you pay up $5, and then if you have around 10 to 20 number of your own images, as I was showing for those stunning AI profile pic, you can actually train it and get those images out there, right?
So creating amount of profile picture is like again a training process.
So training process, which you don't have to worry about because that the entire architecture is ready. You just have to upload all those images out there, and whatever architecture that we talked about, it will just train it for you and then give you the results.
How many images will it be required to train?
What so this particular like a Dreamboat, like the person who is behind it, like his name is Abhishek Thakur. He's a Kaggle grandmaster, so he is working actively on that. What he says is that ideally you would require 10 to 20 images should be good enough for you to train upon. Like it's more like your model is trained enough. You just have to chip in the model and it gives you the.
Do you need to train it? Because the training here needs huge amount of processing.
Yes.
Can you, and the model is free, it released.
Yes.
Can you do transfer learning if you want to adopt?
It's more like transfer learning that generally, ideally, what you do in Dreamboat, it's more like a transfer learning. You have all the weights that are much more refined. You just need to take up some amount of images and do a transfer learning so that it customizes it corresponding to your own original images.
And what about Stable Diffusion? Because here I have clip, I need to retrain the clip also. I need to...
Ideally not, like because as I told you in the very beginning, the individual architectures are already trained, right? And if you talk about clip, as I told you, like there are almost a billion of images that you have already trained upon.
And that's what I say. If I generate cat, I think the color of the cat will be the average color of the database. The balancing will be from the database. And if I want to adapt it, and if I would like to make it more customized to my database, I would need to train it. So I people, I don't think we have the amount of computation ability to train Stable Diffusion from zero.
It will not be possible.
Transfer learning.
Yes, that's
the
true.
question is if you think in your professional opinion it is feasible to train it to some amount of 10K images, which I would like to adapt. Maybe there are new images, I don't know. Database of cockroaches of different colors.
True. Yes.
And using it feasible to train all the elements of Stable Diffusion?
Ideally, like, you won't like if like because I have also not trained. So my assumption is you don't have to train for all the individual architectures. Like as you rightly said, if you take up the clip, right? You just think of that particular clip where you have trained it for billions of images. What the output of the clip, what it does is that it just gives you the encoded images, right? So you don't need to train clips specifically as such. The only thing maybe you might need to train specifically for your own use case might be a denoiser technique, which actually removes noise, or maybe a unit specifically to our use case. Like we talked about the possible use case, maybe creating a digital art. That's a particular specific use case or a domain specific case that we are talking upon, right? Or let's talk about AI, creating an AI picture, right? So in that case, only the two components which I think like maybe the denoiser part or in fact, I would rather say the autoencoder is also something that might not be as useful enough for training, because autoencoder, if we just look at the theoretical aspect of it, the purpose of the autoencoder is just to reduce the size into dimension, right? The only thing that might you might need to train would be the denoising part, which is very specific to your domain use cases.
So I think it's feasible on regular GPUs.
So something that I like feasible, but I don't know like how do they actually provide training and do custom.
Sure did
no one.
Learning for the Stable Diffusion. It's very new. It's
Very relatively new. Yes.
Thank you.
Okay. So yeah, so I thought like because it's a very relatively new concept, I thought why not share with you guys the different like YouTube videos that I have gone through, right? Eventually, if you guys are like following fast.ai, which is a particular community taken up by Jeremy Hayward, Professor Jeremy Hayward from University of in Australia. He actually released 4 parts of the Stable Diffusion lecture, which are very useful, and I actually took up a lot of concept and a lot of learning from that. You can actually take that as a reference. I'd also like to acknowledge a particular video from Lightning AI or PyTorch Lightning. They have a YouTube page where Daniela has uploaded a Stable Diffusion lecture where he demystifies those particular things for you, right? So you can actually look out for those particular YouTube videos, and also look at there are many Medium articles that talk about it. but not in too much of the mathematical or the core architecture behind it. So I thought, why not give a core architecture overview of those stable diffusion as such, right? So happy to answer any question if you have. So that's it from my
So
side.
one question is, can you reiterate the point? First question is, what is diffusion? Like, which step is mainly the diffusion and why is it called stable? Is there some convergence issue that would have happened if that stability module was not?
So why do we call stable? I'll answer that first part, right? Talk about like when you do an hyperparameter tuning of the different n number of steps, right? The first step that you take up a random images, right? You don't know when you're the one that you say, let's say an astronaut writing from an image. And if you look at the first year lecture also, what the article that they have like given for our audiences, when you see that, you would rather find that given a particular noisy image, given after a certain number of steps, you would rather find the image to be good but not that great, right? So at a certain point, when you like with certain amount of training that they have done throughout, right, they came up with an optimized steps as, let's say, 50 or 75 step would be a point where you get a relatively stable images in that word, what you call as stable, where the image will make more sense to you, right? Diffusion, as in like comes from the word diffusion, where you generally like talk about the physics diffusion, where the particular point or smell spreads throughout the room, right? It's more like diffusion model, where given a particular noise, you just try to remove the noise that are there throughout, and then you try to make sense of the noise from the particular architecture that you have seen, right? It starts from noise, but just imagine from how beautifully it actually generates a particular image from that particular noise that you see. So more in that terms, why you call it stable diffusion.
I have a general question.
Sure.
Like you told stability on this thing. Now, how does it runs in production? Like it requires too much of GPU and computation time. In production, how does it scale? Like how does it work?
Ideally, like you when you talk about production or inference time, like as I told you, like ideally any type of images or that you take a random noise, and the first step, you are actually removing that the big dependency of having a very large images, right? You just convert that into very small latent, right? Now when you just think of an MNIST data, right, is the had you worked on MNIST data set, it was just 28 by 28 size, right, the pixel size, and when you train it, you could have trained it much more quickly. Just think of this particular latent. Ideally, when you go into the literature survey of that particular latent, it's just 64 by 64 size, right? You can just take up that particular latent and then pass it through the diffusion, which removes the noise, and then gives you the output. Ideally, like in the inference time doesn't take that long. Like it would what I've tried out in my own capacity to generate an images, it ideally takes around 20 to 30 seconds to generate an image. Yeah, sure.
So when you said there's a graceful cat, graceful swan, and on top of that you had a laughing or a beautiful swan. So there are two different things. But when you're saying that it will take that also, like beautiful swan is like one of the same thing because swan is common, so forever is the case. But in that case, like it's not giving the exact figure.
Okay.
But the graceful might, in case of graceful, it might mean something else. In case of
Beautiful or something.
like, I'm just giving
Analogy.
So in that case, like there would be some other difference, like sad cat and a happy cat, for example. Cat is similar,
True.
but then sad cat and happy cat is a two different things. So if the result is taken according to the cat, then it's not the exact that is being found.
Okay.
So in that case, the output is wrong, like in sense.
So ideally, what we generally find out, like now we are going into the text encoding. So you would just take some amount of time of yours, right? So when you go for a text encoding or like a sad or a beautiful or happy or like, then you have a cat, right? Ideally, what you do in case of a text embedding is that you have billions of words in a particular, let's say in a dictionary, right? Corresponding to that word, you have those indexes and out there, right? Now, yeah, like if we go through the normal architecture or how do we do an embedding matrix, right? A particular word will have certain number of features, let's say 512 features, right? Each of this may be a linguistic feature or visual features out there. So now when you say sad or beautiful, right? Like those particular word out there may have some amount of representation in sad or in beautiful.
Or some characteristics will be there similar.
Yes. So now, just I'll give you another analogy. Now think of two fruits, apple and oranges, right? And I'll take a few more examples just to clear that out. Apple, oranges, king, queen, man and woman. Now let's take up one particular feature called gender, right? Apple and oranges doesn't have any gender. That's a NaN value for us. But then like men and women, men I know one, and let's say I represent the negative gender as 0. That's again king. I know that's a masculine gender, so that's again 1 and 0. But then if I say fruit, that is another feature. So in apple and oranges, I would rather have 1, but in man, woman, king, and queen, we might have no value. So in that way, each particular textual representation of one particular word called beautiful, sad, or that would have some linguistic or any type of features out there, which when you combine with an image, like where you saw an image encoding and a text encoding, when you just combine them together, ideally it will understand, okay, some amount of the image information, like as you said, a sad cat or a happy cat. You know that a cat represented by a text and an image for both of them should match. While a beautiful and a sad, the encodings would be different. So you might have a particular combined encoding, which in case of a beautiful cat will have maybe say 010001 or something like that. Or in case of a sad cat, it would be 001, something like that.
Okay. Apart from images, if it is just text, and if I want to just understand the text and the output should be text. So in that case, how does that work? For example, acha word is good in Hindi as well as acha is okay. So in these, like if acha is only written, then how can you differentiate that it's meaning good or it's meaning okay?
Okay.
I am doing something similar to this.
Like I don't have much context about NLP, like, but what I understand is that like maybe there would be some linguistic features that describes acha as like okay or good or as such, right? So don't have much context into it, so I would not give her like a wrong interpretation of it.
Maybe because I am doing something linguistic,
Right.
I just can give you these examples.
Ravindra, do you have some idea?
Maybe you can use the word to vec or any embedding to create so you are creating the encoding of the word as a maybe one-hot representation in this model. Okay, so maybe what you can do is learn the linguistic features and feed the embedding of that here. So it will have the benefits of both worlds. You first learn the linguistics text, embedding from that using any model, and then we will feed that embedding here in the at the text. So in the embedding of the text, feed that. So now the text is learned, and now the text is now closer to the image. So the word sad is learned from the context word, as well as sad is learned from the image.
Okay, in terms of linguistics, there's only one word. So how and from whom it is matched? Was my I wanted to understand the person who is already into this, like particularly in NLP, so that he can just understand. If there's only one word, how can you understand it's meaning this or it's meaning
learn like normal NLP, like word, and then also learn it using the image features.
Okay, any more questions?
So I think that's a very similar thing, if that's correct, like very similar. Is it using the same architecture or something?
It uses clip, yes, but if I talk about what architecture does it uses specifically, I'm not very sure. I'm not
But something very similar.
very similar to that.
So one question is, does the length of
You can speak into this.
does the length of the text have an impact on the inference of the output? Because we have seen examples of very complicated text to generate the image. So does that have any play into how much time?
Like I would rather answer this in a much more practical sense. Just think of it like a beautiful, like a astronaut riding a horse. Whatever encoding that you get, it would be for particular fixed size, or a particular what I showed you in old man wearing a glasses with 4K neon HD and then like neon color, right? All those text all together will create an embedding, which would be much more like representative of what you are trying to speak, right? So I don't think so. Even if you give a longer text, because so there is a particular website called lexica.art. You can note it down. Lexica.art. It has generated billions and billions of images out there using Stable Diffusion. And if you click on one of the images, right, you can actually look up like what are the texts that you have shown. So for certain images, you will get very small the context out there. For some other images, you would see a very large context, like astronaut riding a horse, neon, ambience, bright colors, focused images, and as such. Like when you give up more and more number of text, but eventually the context embedding would be more or less similar, right? It would try to represent it and represent in that context embedding.
So far the examples we tried out, they were decently represented.
Okay.
We need to see. I mean, we need to see when it will fail. But that's interesting, no? The typical research mind of thinking. Why does it work and when does it fail and what is the limit scale?
Thank you.
So yeah, I would be happy to answer or collaborate with you all if you wish to. I'll also put up my email ID along with Ravindra Babus. If you want to collaborate with us, you're open. So thank you so much for attending and coming on. Thank you.
Thank you.
I'll try to like open source the slides.
Video is available on YouTube. Right?
Yeah, the video is also available.
It takes about a week also to upload. We need to do some pre-processing.
Thank you guys for attending the DevDay. Is there any questions in the chat?
No.
Before we wind up for today, we had participated in the Hacktoberfest of 2022. And Hacktoberfest, as you all know, is a celebration, month-long celebration of open source and open source projects, contributions, and contributors. We conducted several events, workshops, and we have 2 winners. The criteria was to create a PR which gets accepted to an open source project. And we have 2 winners. One of them is Tarun Jain and Choudhury. Thank you so much. Congratulations. And we have a small token of appreciation from Suraj, is a personally customized branded t-shirt and other goodies. But I'm going to show you, if you can please.
We can come this way.
You can have this.
Since we have Tarun in-house, if you could just talk about the experience or how you went on with your work, short words, just to motivate others to, when open source contribution is creating its secure. Yeah, please.
So hello, I'm Tarun. Basically, when you start with open source contribution, most of them try to get into code stuff. But as you know, Hacktoberfest is only for 1 month. In starting 10 to 15 days, I tried to contribute to some open source repository where you can contribute documentation. In documentation, you don't need to write any code. So, but the criteria of getting selected for this competition was give a valuable contribution. So as Sir said about Hugging Face has many open source contribution or repositories. One of them is SKOps. So SKOps is something where you are doing SQL operations in production. Like Hugging Face is something like if you have any machine learning models, you want other people to come and use that GUI version of it. So they have many projects. I was one of the contributors to that. There is called Keras working group. We are trying to build Keras. There is a documentation. We are trying to build the models GUI version using Gradio tool. So this is where I contributed the code part after 15 days. First 15 days, I concentrated only on documentation, which is really worth getting into open source. Like if you want to get into open source, try with documentation, because if you get into code stuff contributing using code, you will get stuck or you might get frustrated. So start with small contributions and then get going. Thank you.
Thank you so much for attending.
Thank you.
So we'll go to the panel. What are you going to, next?